Swayam Prabha. Digital India. Educated India.
Welcome back to the manufacturing automation course. So let me remind you that last time what we have discussed and where we started discussing is the center board hopper feeder. So this is also one of the feeders for feeding small engineering parts to the assembly machine. That's what we said. Now here if you look at this diagram, we have the hopper, and in the hopper we have the mass of parts, and particularly this kind of a hopper is suitable for feeding cylindrical parts. So through the mass of the part, as we said, that there is a blade which reciprocates, it goes up and down, and while going up and down through the mass of the part, on the track of this blade the parts will be nested, small parts will be nested, and at the topmost position of the blade, when the blade will be aligned to this delivery chute, then all the parts will be sliding to the chute and going to the assembly machine. So this is a simple design, and the basic thing to be designed here is the angle of the blade. Now here one thing that we started discussing last time is that when the blade will be coming from the position below to the top, then it will in the halfway it will start, first it will accelerate, and somewhere in the middle it will start decelerating. So there is a limit to the deceleration, because if it is very high, in that case the parts located on the blade will be thrown out. That is one thing. Now for a certain deceleration, therefore, which will be optimal at which value the parts will not be thrown out, when the parts will be located on the blade, particularly on the upper position of the blade, then the angle of inclination of the blade, or the maximum angle of inclination of the blade is an important factor, because if the angle of inclination is more, in that case what happens is that it will facilitate the parts to go down the track. This is one thing. But at the same time, if the angle of inclination is very high, in that case it will take more time for the reciprocation of the blade, and so the production rate will be lower, because the production because the time taken will be higher, and the rate always is won by the time. That is what we discussed earlier also. Now here an optimum value of track inclination angle exists, and theoretically it can be shown to be function of only the dynamic coefficient of friction and Rb by L. So Rb, we said that this is the pivot radius, and the L, small l, is the length of the track. So the length of the track in which the parts will be nested, okay, and of course the maximum number of parts which can be nested here will be defined by the small l divided by part length, which is capital L. Okay. All right. Now here this diagram we started looking at last time. So this is when the part is located at the uppermost position of the track, and these are the forces which are acting. This is the mass of the part, okay, and this is the reaction, that is the normal force imparted on the part, and this will be this is the Rb, and the total length is the Rb. So the length of the part is capital L. So therefore this length from here to here will be Rb minus L by 2, if we consider that this point is located at the middle of the part, let us say, and this is the angle of inclination of the blade or of the track, okay, here. Now this is the position of the part when it is sliding down. All right. Now while sliding down, the forces acting will be the normal force N1, this in the free body diagram, this is the linear acceleration A, and mpg is the mass of the part, and here this is the force which will be the friction force which is resisting the acceleration of the part. So, here in fact reaction between the track and the part to become 0, for example. So, we say that the n1 has to be equal to 0. So, for n1 has to be 0, let us write down the equation first, that n1, this is that n1 actually, this is n1 minus mpg cos theta m, which is acting in this direction, is equal to mp theta, this is the acceleration, this is a Newton's law. So, mp theta 2 dot, this is the acceleration, into rb length, rb minus L by 2, rb minus L by 2 is this length, all right. Now, this from this equation mp n is n1 to be equal to 0. So, mp theta 2 dot rb minus L by 2, this has to be equal to minus mpg and the cos theta m. So, from here what we can find out is the acceleration. So, this acceleration will be g cos theta divided by rb, okay, from this equation. Now, let us assume that for simplicity that during the period of the upward motion of the blade, the drive to the blade is designed to give a constant acceleration and a constant deceleration. The values will be that we found out here, and this is the g cos theta divided by rb. So, what we are saying once again, that when the blade is going from the lower position to the top, it will go at a constant acceleration and a constant deceleration. The values of both acceleration and the deceleration will be g cos theta by rb. Now, under these conditions, the total time t1 taken to lift the blade so that the track is inclined at an angle theta m. So, this theta m we said here, let us say this is the theta m. Okay. So, for that theta m to the horizontal, this is given by t1 square is equal to 4 rb theta m divided by g cos theta m. Okay. So, it is coming from actually if L is equal to half a t square. Okay. So, the t square is equal to 2L divided by the acceleration. So, the L here is the rb. Okay. T square is equal to 2L by a, or here we can say that this is, it can be also theta m. So, g cos theta m divided by rb, this is the one that we have here as that acceleration or deceleration. So, therefore, t1 square can be given by 4 rb theta m divided by g cos theta m, all right. So, this is coming from, once again, the theta m can be written as half of the a t square, and the t square is 2 theta m in that case divided by acceleration. So, this is the acceleration is given here, and we are taking the theta m here. So, the t square will be 4 rb theta m divided by g into cos theta m. So, it is now assumed that when the blade is in its highest position, it dwells for a time t2. See, earlier we decided that we have discussed that when the blade is going up, it will dwell for some times because all the parts need some time to slide. Now, this dwelling time, it should be long enough to allow at least one part to go from the top position to the entire length of the blade and coming to the exit, that is coming to the delivery chute. This is given in the worst case as it is written here, by the time taken for one part to slide the whole length of the track. Okay. The forces acting on a part under these circumstances are given here. So, this we have seen. Okay. These are the forces which are given when the parts are sliding down. This can be written as mp into the linear acceleration is equal to mpg sin theta m minus mu d mpg and the cos theta m. Okay. So, this is given by, from here you can see that this is the mu d mpg cos theta m, and here it will be mpg and the sin theta m. So, the difference between them, okay, because these are two in the opposite directions, different directions. So, this is given by equal to mp into the acceleration. So, this will be the equation when the part is going down. That means this is the force which is the friction force, and this in this direction this will be the force which is mpg and the sin theta m. So, these two differences will be equal to mp into the acceleration, which is that a here. Okay. So, from this, all right, where this a is the linear acceleration, as we said, of the part down the track, and mu d is the coefficient of dynamic friction between the part and the track. So, the minimum dwell period, then T2, from here you can find out the T2 can be given like the T1 we have said. So, this will be the 2L divided by the acceleration. The acceleration we could find out from here, okay, that A is equal to mp is getting cancelled from everywhere. So, this will be g and the sin theta m minus mu d and the cos theta m. This is the acceleration that we are getting. So, therefore, this value we can put, this acceleration, that will be 2L divided by acceleration, because that L is equal to half a t square again. So, the t square is equal to 2 the length and the a. So, the a in this case is this, all right, this is the acceleration, and 2 into L is the L being the length of the track. Okay. So, therefore, we can find out that what is the dwell time. Of course, the dwell time T2, this will be the whole thing to the power half, that is root over this one. This is the dwell time, okay, T2. We had the T1, which is the time taken for part to go up, all right. Now, for simplicity, we are saying that the time taken to return the blade to the lowest position from the up position is the same as the time taken for the blade to come from the initial position to the top position. They are the same. So, therefore, the total time that will be taken will be equal to going up, going down. So, T1 plus T2, this is 2 T1 plus the dwell time that it is stopping for sometimes for the parts to slide down the tracks. So, the total time will be 2 T1 plus T2, which is given by 2 into this is the T1 that we found out, and this is the T2 that we found out, all right. Now, if we look at this equation, all right, you will see that these two terms, that is the first term and the second term, they are actually quite different in the sense that one will increase with the increase of the theta m, and another will decrease with the increase in the theta m. Okay. So, for example, this is increasing, this term is increasing with the increase in the theta m, and this term is decreasing with the increase in the theta m. So, therefore, an optimum value of theta m will always exist, that gives the minimum period Tf, that is the total time, and hence a maximum theoretical feed rate, because the theoretical feed rate or the overall feed rate will be defined by the time taken for the blade to come up, that is time taken for the blade to complete a cycle. Cycle is going up and coming down, including the dwell time. It can be shown mathematically that this optimum value of theta m is a function only of the mu d and the Rb by L. Okay. The maximum number of parts, I just told also this, that may be selected during each cycle, that will be the small l is the length of the track divided by the capital L, which is the length of the part. So, the small l by capital L, this will be the maximum number of parts that may be selected during each cycle. In practice, the average number of selected actually will be less than the small l by capital L, because not all the time the part will actually all the parts will be taking or nesting on the track, meaning the track will not be filled up fully, okay, during each of these cycle. So, therefore, there is a concept of the efficiency of the bowl feeder, and that efficiency can be experimentally measured. That is, this bowl feeder, any bowl feeder that you are selecting or designing, it has to run for several times and see how many parts on an average is coming on the track, all right, because as you understand that small l by capital L, this is the maximum number of parts, that is when the track is filled with the parts, but not all the time the track will be filled up, and therefore, that efficiency it has to be multiplied by that efficiency. So, therefore, the mean feed rate f, this will be equal to the n, which is the frequency of the blade, into the efficiency and the small l by capital L, which is the maximum number of parts which is coming on the in one cycle. Now, the blade frequency n, this is given by 1 by Tf. So, frequency is always 1 by time. So, this Tf is the total time taken for the blade to go up, coming down, including the dwell time. In practice, the value of efficiency must be obtained from experiments. As I said, that it has to run for some times and find out what is the average number of parts which are being taken in the cycles during the blade coming up and down. Let us take a numerical example. Say a center board hopper feeder has a blade length of 200 millimeter. This is just an example, all right. 260 millimeter, and it is designed to feed cylindrical parts end to end. The center of rotation is 250 millimeter from the lower end of the blade track. This is the pivot lower end. The inclination of the track when the blade is in this highest position is 45 degree, and the coefficient of sliding friction between the parts and the track is 0.3. Calculate the cycle time of the blade for the upward motion of the blade. I will remind you that for reaction between the track and the part to become 0, we will write that equation, the Newton's law, Newton's second equation, that n minus mpg cos theta m, this is equal to mp acceleration and the length, that is rb minus L by 2. Or from here we are getting that the acceleration is g cos theta by rb. So, to lift the blade, that is the time taken for the blade to go from the initial position to the topmost position, this will be given by T1, which is 4 rb theta m divided by g cos theta m, and this will be root over if it is T1, and similarly the T2 dwell time, it will be given by this, that we have seen earlier. So, therefore, the total time taken is 2 T1 plus T2. I am reminding you that how we have derived the theoretical formula. So, this is the total equation, that is for the total cycle time. Now, here we are putting RB, this will be equal to 260 plus 250, because going back here what we are saying is that the center board hopper feeder has a blade length of 260 blade length, and from the lower point of the blade up to the pivot is 250. So, the entire RB will be 250 plus 260, okay. And the theta m has been given as 45 degree, which is 0.785 radian. G we had taken as a 9810 millimeter per second square, acceleration due to gravity. The length of the track given is 260 millimeter, this one, and the mu d is 0.3 millimeter, 0.3. So, you put all these values here in this equation and we will find that this will be equal to 1.29 second. So, 1.29 second, within 1.29 second the blade will accelerate, it will start decelerating, it will stop for some times, then again it will accelerate and decelerate and going back to the initial position. So, this time is the Tf going up, dwell and coming down. So, this is in this example it takes 1.29 second. Hope it is clear. Now, the next hopper feeder, this is the reciprocating fork hopper feeder, and if you see here the difference between the reciprocating fork hopper feeder and the one that we have earlier seen, that is the center board hopper feeder, is that here the fork which is reciprocating, it is actually taking up the parts, and this fork it has a slot, and this slot, on this slot the headed parts will be hanging. So, this kind of reciprocating fork hopper feeder, they are actually suitable for feeding the headed parts like the bolts for example, or rivet with the heads for example. So, those heads will be hanging here because there is a slot in this, and when it is coming through the mass of the part here and going up, it will take up some of the parts, and then here it will dwell for the parts to slide down this track, and then this is the delivery chute. When it is aligned with the delivery chute, all the parts will be sliding from the track to the delivery chute. Now here, for the purpose of the better feeding, the ball is rotated and it is also inclined at a certain angle with the vertical axis. Okay. This is to facilitate the parts to go to this fork when it is reciprocating actually. Analysis for maximum fork inclination and the maximum rate of reciprocation, this will be, as you understand, similar to that of the center board hopper feeder, because here in this case what is happening is that this fork from the initial position it will start accelerating, okay, and on the midway somewhere it will start decelerating, and then it will stop for some times, that is a dual period, dual time, then it will start accelerating, and somewhere in the middle it will start decelerating and going back to the initial position. So all these factors that we have considered in the center board hopper feeder, that is the deceleration has to be limited, because otherwise again the parts will be thrown out when the parts are located particularly at the topmost position of the fork, and for a certain deceleration we have to limit the track inclination angle, because at a higher angle, although the parts will be facilitated to be sliding from the track, but it will take more time. So the cycle time will be more, and therefore the production rate will go down. This is a new kind of hopper feeder which is different from others that we have discussed. This is called the external gate hopper feeder, and as the name says that external gate, there is an external gate through which the parts will be falling. So the design of this feeder is quite simple. It has this one, as you can see in this drawing, this is the stationary plate, and on this stationary plate we have a stationary outer sleeve connected. This is rigidly connected here, and inside that there is a rotary inner sleeve. This inner sleeve is rotating inside the stationary outer sleeve, and there is a gap between the rotating inner sleeve and the stationary outer sleeve, and in the rotary inner sleeve there are slots cut like this. In this section it is shown. So the parts are, mass of the parts are located at the base of the rotating inner sleeve, and when this is rotating, the parts, small engineering parts, as we said, cylindrical parts, they will be nested in these groups, and when these groups will be aligned with the external gate, the parts will be falling one by one. This is the idea. So once again, there is a stationary outer sleeve, inside that there is a rotary sleeve which is rotating. In the rotary sleeve there are grooves. So the mass of the parts at the base of the rotary inner sleeve, and the whole thing is inclined to the horizontal with at a certain angle, let us say here, as it is shown in the figure. And when this rotating inner sleeve will be rotating, the parts will be nested in the groups here, and whenever during the rotation the groove will be aligned to the external gate, the parts will be coming out of the gate one by one. So this is the whole entire functioning of the external gate hopper feeder. This is quite popular. This is also used in industry for feeding the small parts, small engineering parts to the assembly machine. So here maximum feed rate is determined as a ratio of the velocity and the center line distance between the adjacent slot of the cylinder, meaning that whatever we have the velocity here of the rotating inner sleeve, that will be divided by the distance between the sleeve, okay, inner distance between inner adjacent slots, and that will determine the maximum feed rate of the feeder. Let us take an example. Let us see that how it is actually decided, how it can be obtained. Now at a limiting velocity v, velocity of the rotating inner disc, at a limiting velocity v, the part will neither fall through the gate nor pass over, but will become jammed between the corner B and the C, okay, of the slot and gate. This is the slot and this is the gate through which it is coming out. This is the external gate. So if the velocity is certain, velocity is at a particular velocity, or it is a limiting velocity, the part will neither fall nor it will actually go through. So, it will be actually clogged here. Okay. It will be jammed between the corner B and C of the slot and the gate. At any velocity below V, the part will drop through the gate, and if the velocity is more than the limiting velocity, by inertia the part will actually pass through the gate and it will not fall in the gate. So, how we are getting the finally the conveying velocity, as we said, by dividing the velocity with the center line distance, that we will discuss in the next class. Thank you.